Bismillahirrahmanirrahim. In this video, I will explain how a motor neuron excites the skeletal muscles. Let's start. The site where a motor neuron's terminal meets the muscle fiber is called the neuromuscular junction. The neuromuscular junction is an example of a chemical synapse. At the neuromuscular junction, the presynaptic motor axon is no longer covered in myelin sheath. Here, the presynaptic axon gives multiple branches called the synaptic terminals. The synaptic terminals have small bulges called the synaptic end bulbs. The synaptic end bulbs contain neurotransmitter acetylcholine. Some of these vesicles are gathered into groups of 50 and are positioned at active zones close to the nerve membrane. A 30 nanometer synaptic cleft exists between the nerve ending and the skeletal muscle, and it contains a meshwork of acetylcholine esterase enzyme. The skeletal muscle membrane or sarcolemma at the junction has invaginations called post-junctional folds, which increase its surface area facing the synaptic cleft. The post-junctional folds form the postsynaptic motor end plate, which is studded with acetylcholine receptors. When an action potential travels along the axon of a motor neuron to terminate at the neuromuscular junction, the axon terminal releases acetylcholine. The acetylcholine molecules diffuse across the synaptic cleft and bind to acetylcholine receptors on the postsynaptic motor end plate. Once acetylcholine binds, a channel in the acetylcholine receptor opens and allows positive ions to pass through into the muscle membrane, causing it to depolarize. This depolarization is called the end plate potential or EPP. The end plate potential activates voltage-gated sodium ion channels, causing increased sodium ions to enter the muscle fiber and trigger an action potential which rapidly spreads along the entire membrane. Meanwhile, the acetylcholine in the synaptic cleft is degraded by the enzyme acetylcholine esterase so that the acetylcholine cannot rebind to a receptor and reopen its channel, which would cause unwanted extended muscle excitation and contraction. In the sarcolemma, there are periodic invaginations called the T-tubules or transverse tubules. The T-tubules transmit action potential deep into the sarcoplasm of skeletal muscle in the vicinity of sarcoplasmic reticulum and the contractile proteins. The tubules of sarcoplasmic reticulum run parallel to the contractile proteins and closely surround them. Terminal cisternae are bulbous portions of the sarcoplasmic reticulum with stores of calcium. Two terminal cisternae and one T-tubule form a triad, which is a threesome of membranes having sarcoplasmic reticulum on two sides and the T-tubules sandwiched between them. The triad surrounds the cylindrical myofibrils, which contain contractile proteins, actin, and myosin. The term excitation-contraction coupling confuses many students. It comes down to this. For a skeletal muscle fiber to contract, its membrane must first be excited in the form of an action potential. The wave of action potential which sweeps along the sarcolemma is coupled to the muscle contraction through the release of calcium ions from the sarcoplasmic reticulum. Release of calcium and its interaction with muscle proteins is a critical step in the skeletal muscle contraction. When the skeletal muscle is at rest, calcium is stored inside the sarcoplasmic reticulum. Action potential of the T-tubule causes current flow into the sarcoplasmic reticular cisternae where they abut the T-tubule. The voltage change is sensed by dihydropyridine receptors present in the T-tubule. Activation of dihydropyridine receptors activates calcium release channels called ryanodine receptor channels in the adjacent sarcoplasmic reticular cisternae as well as in their attached longitudinal tubules. Ryanodine receptor channels remain open for a few milliseconds, releasing calcium ions into the sarcoplasm surrounding the myofibrils and causing activation of the contractile proteins. Muscle contraction continues as long as the calcium ion concentration remains high. However, a continually active calcium pump located in the walls of the sarcoplasmic reticulum pumps calcium ions away from the myofibrils back into the sarcoplasmic tubules. This pump, called SERCA, which stands for sarcoplasmic reticulum calcium ATPase, can concentrate the calcium ions about 10,000-fold inside the tubules. In addition, inside the reticulum is a calcium binding protein called calsequestrin, which can bind up to 40 calcium ions for each molecule of calsequestrin. Ordinarily, each impulse that arrives at the neuromuscular junction causes about 3 times as much end plate potential as that required to stimulate the muscle fiber. Therefore, the normal neuromuscular junction is said to have a high safety factor. The high safety factor ensures that muscle contraction does occur each time a signal is sent by the motor neuron. When the nerve fiber is stimulated at rates greater than 100 times per second for several minutes, it diminishes the number of acetylcholine vesicles so much that impulses fail to pass into the muscle fiber. This situation is called fatigue of the neuromuscular junction. Neuromuscular fatigue has the same effect that causes fatigue of synapses in the central nervous system when the synapses are overexcited. Fortunately, under normal functioning conditions, measurable fatigue of the neuromuscular junction occurs rarely, and even then only at the most exhausting levels of muscular activity. Thanks for watching and listening. Do share this video with your friends and colleagues. If you like this video, Subscribe to this channel for watching more videos.